How do you manage clock skew in large synchronous digital systems? Imagine a busy city where traffic lights change at exactly the right moment to keep everything flowing smoothly. Now think of a large digital system where the clock signals are like those traffic lights. Managing the timing so all parts stay in sync is a big challenge. When the clock signals arrive at different parts of the system at slightly different times, that's called clock skew. If not controlled, it can cause data to be latched incorrectly, leading to errors or slower performance. So how do engineers keep everything running in harmony? First, they design the clock distribution network carefully. They use balanced clock trees or clock meshes. A clock tree splits the clock signal evenly so that all flip-flops and registers get the signal at nearly the same time. Think of it like a well-planned road system that avoids traffic jams. Clock meshes are like a grid of wires that supply the clock from multiple directions, helping to even out delays and reduce skew. Matching the length and electrical properties of these wires is also key. Longer wires take more time, so keeping them uniform helps keep the clock signals synchronized. Next, buffers and drivers are added at strategic points. These are like traffic controllers that boost the clock signal strength, making sure it reaches all parts of the system without delay. Proper sizing and placement of these buffers help prevent skew caused by weak signals or signal degradation over long wires. Engineers also use special circuits called phase-locked loops and delay-locked loops. These circuits can adjust the timing of the clock signals dynamically. They shift the phase of the clock so that signals arriving at different parts of the system are aligned perfectly. It's like a conductor adjusting the tempo to keep the orchestra in sync. Physical placement of flip-flops and registers is another important factor. They are placed close to the clock source or along balanced paths. This reduces the length of the clock wires and minimizes delay differences. Grouping registers that work together also helps keep their signals synchronized. Temperature and manufacturing variations can cause delays to change. To counter this, designs include guard bands or adaptive techniques that adjust timing based on operating conditions. This way, the system remains reliable even when things heat up or when chips are made with slight differences. Timing analysis tools are used during the design process. These tools simulate how the clock signals behave and help identify potential skew issues. Sometimes, engineers intentionally add a small amount of skew to critical paths to give signals more time to arrive. This is called skew balancing and helps prevent timing violations. Finally, flip-flops and registers are chosen for their ability to tolerate some skew. Techniques like clock gating and crossing clock domains also help isolate parts of the system from skew effects. In systems with counters and flip-flops, managing clock skew is vital. It ensures that data is latched correctly and that counting sequences stay accurate. Without proper control, the entire system could slow down or produce errors. So, from designing the clock network to using special circuits and careful placement, engineers have many tools to keep large digital systems running smoothly. It's all about making sure that the clock signals arrive just in time, every time, to keep everything working perfectly together.